here's some data. We'll collect data, like I said, on Wednesday, I think. Here's some actual data. It's some dated data. We'll come back to that. I've got some more current data, but I don't want to base our current data just yet. I want to work off of this first. What I've done, USA Today put this back out, I think it's back in 2001. And we're going to update this, don't worry. This is the previous data. The people in the United States under age 65 with no health insurance. No health insurance. And this even predates Obama. Or Obamacare, anyway. So here are the years, 92, 94, 96, 98, 2000. That's the number, estimated number of people without health insurance in the United States. Okay. What are we looking at on the right-hand side, the right-hand T-table? These are called T-tables, XY tables. You've seen these many, many times in your math classes. Many, many times. Very often it has an X and a Y here, which is totally fine. I personally like to have it with some kind of a descriptor on it. That way the reader knows what they're looking at. So what's over here?
Condensed version.
Say that again.
Same thing.
Condensed.
Exactly the same thing condensed. Exactly the same thing condensed. Instead of putting the actual years in, you've got years since 1990. That's totally fine. Nothing wrong with using the years, especially because the machines are going to be doing the math for us. But this is very nice. Not having to data enter all those zeros. You just cut yourself out. What is that? 30 zeros you don't have to type. Fantastic. All right. Describe for me, friends. What do you think is the state of uninsured people under age 65 in 2013? Based off of that data. What is the state of the country right now? Uninsured, no health insurance, under age 65, 2013. What's the state of our nation? See, that's a stat question, isn't it? That's a stat question. I heard pretty poor. Is that what I heard? Pretty bad. Is that what I heard? I heard pretty blah, 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 blah. Snickers. So why pretty poor? And now I'm going to change the question a little bit. You can't use what you've heard in the news unless what you heard in the news was good, sound data collection over the past 20 years. Or in your case, over this decade. So your job is, using only that, make a claim about health insurance, or lack thereof, those under age 65. What are you guys doing? What are you guys doing? Tell me your process right now. I care about the process. I see everybody puts their head down and starts working. Give me some processes. Linda, go.
I did 2013, so I did 13 times 2 to get it, because you were doing 2, 4, 6, 8, 10.
Okay.
And that gave me 26.
Why 13 times 2?
Because we're in the year 2013.
Oh, okay, I got you.
Isn't that what you wanted?
I'm just curious. I was just curious to hear your process. I heard 13 times 2 to where 13 came from.
90, okay.
So, well, I think, can I, before you go any further, I think what you need is you need to figure out which one of these numbers 2013 is.
Right, and that's what I did.
So, it's,
20,
how many years after 1990 is 2013?
23.
23.
Oh, I got 26.
Right, but it's 23 years after 1990. I see what you're doing. You see in the skipping by 2, skipping by 2, skipping by 2. Well, that 10 just represents 2000. So 20 would be 2010. So 23 would be 2013. Is that fair? Don't overthink this column. It's simply a labeling based on these years. And it's a base year of 1990. If you want to make this easier, just use this chart and put 2013 in. That might be easier for you, if that's getting you goofed up. But there's no mathematics to do on the year. The year is 23 years after 1990, and it's the year 2013, depending on which one you want to use. Is that fair? Now, Linda, I interrupted you. Tell me where you're going to go with that. Once you had your number, what are you going to do with it?
I was going to go into statistics.
Mm-hmm.
And then I was going to add it in there.
Oh, well, what were you going to add in there?
I was going to do
whatever that year is.
Like 23.
What are you going to put here?
I just lost it. Hang on a second.
Because that's the question I'm asking, isn't it?
Right.
I'm saying, based off year 23, you said what goes here?
57.
Why 57?
Because I just kind of went, oh no, I screwed that.
No. Tell me what you said right there. What are you thinking of?
No,
Because I just saw something beautiful. Can I erase the board? Yes, I can. Can I erase this, friends? Is that okay?
Yeah.
Okay. Linda, well, you just showed me something very, very interesting. You went like this. You went, what were you doing there?
I was adding 13 onto the 44.
Why would you add 13 onto the 44?
Because it was 13 years.
Now, this is a great learning experience right here. She added 13 onto the 44 to get 57. Now, I'm not saying that there might not be 57 million uninsured people under age 65 in the United States, but why can't we do, why doesn't that make sense if this is 13 years?
Because there's, or that,
It's not consistent.
Well, hold that thought, Andrew. Hold that thought, okay? Please, hold that thought. Why, mathematically, Alan, can't we do this?
Because you can't add years to people.
Because this is people. That's people, this is years, and this is people again. So you gotta watch your units, and that's why, conveniently enough, your next project is called dimensional analysis. Because that's the kind of thing we get so bad at, because we never do it. We never do it in traditional math classrooms. We never analyze units. And we put you out in the world, and we tell you to, like, fix your radiator. Add antifreeze to your radiator. And you have to deal with that. Or to, you know, any manner of things that you actually do in your life, from baking to cooking to cleaning to anything, requires dimensional analysis. We never do it. David, help me!
Oh, I was going to ask if, can you tell me if I'm on the right track? But
I don't know.
Okay.
Go.
Well, if you take the difference between the numbers of uninsured,
Mm-hmm.
and then
So what you're saying is, these guys here?
yeah,
Well, let's do two things if it's okay.
yeah.
What's the difference right there?
2.
Okay, 2 years. Well, two, but I mean, it's pretty much assuming that it's years, because we're here. How about here?
2.
2 years. How about here? 2. Good. And then how about here? 2. Awesome. So we've got a very, very consistent 2-year difference among the x values. David, go.
And then find the difference between the numbers on the right hand.
Okay, so you're going 35 to 38.
3.
Good. And remember what that is? That's 3 million technically, right? I mean, because that's millions of people, so we just increased 3 million people. Okay, Dave, let's keep going.
And then
1 million,
2,
2 million,
and 3 million.
and this is 3 million again, isn't it?
And then find the average.
And then find the average of those. So David's got to vote. I like this. This is slick. This is slick. Nobody's going to say find the average of those differences, because it's fairly obvious that the average is 2, because they're all the same. But if we find the average of these, and assume that that's legit, well, first of all, let's do it. There we go. 3 plus 1 plus 2 plus 3 divided by 4. 9, 4, 2.25, is that what I heard? Yes? So in other words, one way we could look at this is to assume, rather than the uninsured rate increase 3 million in those 2 years, 1 million in these two, 2 million in these two, and 3 million in these two, we can just assume that it increased 2.25 million between each of those intervals. And wouldn't that start and stop at the exact same place?
Yes.
Has to, right? If we increase 2.25 million, here, 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 and here, we would pick up 9 million people over the course of those 8 years, which is exactly what happened. If we only look at the beginning and the end, and that's a humongous if, David. Prove to me that's legit. I love what David just said. I want him to prove to me that it's okay to do that. Or anybody for that matter, prove to me it's okay to do. I don't pick on David. I love your idea, David. I think it's fantastic.
I didn't think that far ahead.
No. And why would you? There's no reason to, right? There's no reason to be that far ahead, because we're looking at a pattern and we're saying these numbers are fairly close-ish. Why not just average them? The problem with averaging, here's the deal, okay? Suppose you analyze Juniper Street, that one we talked about from Greenwood up to Portland. We have College Way and Juniper, both of which basically climb the same distance. They both start at Greenwood. College Way does this, Juniper does my right hand, and they do this. So on average, both of their grades are exactly the same, because they start and stop at the same places. But they couldn't be more different in their shapes, because Juniper starts essentially flat and then rockets up. Yet, on average, they has the same grade as College Way. Right? That makes sense. But that's like saying if you stick your head in the fridge and your feet in the oven, on average you're fine. Because it ignores the extreme. You see what I'm saying? It smooths it out too much when we're talking about juniper. So my question is, were we legit when we said, let's just average these guys down? Well, the only way I feel okay about that is if the data actually looked like it was doing basically a uniform rise.
But it's not.
We can't tell without looking at it. Thank you, David, for proving the point. It might be doing it's not a perfectly uniform rise. This is where we come back to, friends. You have to unlearn some of the stuff you learned in Math 60. Math 60 taught you that perfect lines have perfect points on them. Over 2, up 1, over 2, up 1, over 2, up 1.
Is this what you talk about? There's mathematical error.
There's mathematical error. And when I say error, I don't mean a bad thing. I just mean there's not perfect consistency from year to year to year to year. It could be following a slightly predictable pattern, and we just have to figure out what that pattern is. So, here's what I propose. I want to come back to David's idea. But I want to take a look at a new way of looking at our data. Check this thing out right here. All right, bump this down. Look at this. This right here is the exact same thing you just looked at in tabular form, but it's in two-dimensional graphic form. When it's in a table, like it was back there on the board, well actually it was up there on the board. When it's in a table, it's one-dimensional, which means in order to see those differences you're talking about, Dave, we actually have to go and do the math on they're called the finite differences. We'll come back to that. We'll come back to that. Finite differences. With this, which is called a scatter plot. A scatter plot is a way of putting X and Y data into a visual and then saying to ourselves, you know, that looks blank enough. Blank enough. Is it a quadratic? Is it a parabola? Is it exponential? Is it linear? Does it go up and come down and go up and come down and go up and come down? Is it cyclic? Another fun data set to look at would be cyclic data. So, everybody follow what we're looking at here? Let's make sure we understand. That blue point right there, 2, 35. What is that?
1992.
That is 1992, Jordan. And in 1992, what?
There's 35 million.
There were 35 million uninsured people in 1992. That's what that point stands for. How about this point right here? 4, 38. What does that stand for? In 1994, 38 million uninsured in America. Every one of these points represents one of the X and Y coordinates from our chart. Every one of those points. Fair enough?
Yes.
Is that believable?
Yes.
Okay, good. Was that Hassani? You don't know?
It could be Juniper Street, like right here, and then.
Oh, but here's the deal. I'm showing you the street. Hassani's got a good point. He's like, I don't know, man. This could be Juniper where it level. I'm showing you the street. This is the actual street. This would be Juniper Street. So it is definitely up and down, but it's not. At least not these years. Now Hassani's got a point. Hassani's got a point. Suppose in 1993, the number of uninsured spiked up to 45 million and spiked back down. I assure you that didn't happen. I assure you that couldn't have happened because presidents would be assassinated for things like that if that actually did happen. I mean, if the number of uninsured doubled overnight, people would freak out. And rightfully so. And rightfully so. So, Hassani's point is a good one. But the reason we couldn't do it before is because we were ignoring these 3 points here, Hassani, oh look at the end too. And if those 3 points had come down, for example, like this, and then gone back up, that means the points would follow more of a pattern like that, which would make me think it was more of an exponential behavior than what appears to be a linear one. So David, what I'm trying to say here, kind of a long-winded way, is I liked your average idea. I liked your average idea. I think it was damn good. I think it was damn good. No, I think it's damn good. If I had to pick one of these 3 shapes that best describe that data, what would you guys pick? I would think linear. It appears to be roughly linear. It's not perfect, is it? It's not perfect. So our job now, who wants, I'm going to take this out momentarily. 2.25, I'm trying to remember that. So we have one vote. I'm going to write that. Actually, I'm not going to try to remember because I won't. I'm going to put it here. David, your vote vote for rate of change of uninsured. Now careful, I erased it now. The vote was for an increase of 2.25 million over how long? Gotta remember, 2 years. That's over 2 years, right? 92 to 94, 94 to 96.
I divided it by 4 and I got 6.5.
Say that again.
So I did 2 plus 2 plus 2 plus 2, and then I divided it by 4 and I got 6.5.
Wait,
That's
describe,
5
say what you did again.
She did the
I did,
years.
I did the years,
So 2 plus 2 plus 2 plus 2,
right?
divide by 4, is 2.
Let's divide by 5.
There's only 4 of them
It's by 4.
There's
and I-
5 years, but
I
there's
got
4
6.5.
differences. There's only 4 differences in 5 years. Remember, when you find those differences, you're between 2 years. So you lose one of the, there aren't 5 anymore when you look at, we only had 4 different, I erased it now unfortunately. Let's go back to the data list up here. When you're looking at the years here,
Yeah.
the difference here is 2. The difference here is 2. The difference here is 2, and the difference there is 2. There's only 4 differences. Just like there were only 4 differences in the uninsured.
But you're saying to divide it by 4, right?
No, I'm saying divided by 2, because that average of 2.25 million we came up with was based on looking at the differences between 2-year periods. Does that make sense? It doesn't matter what year period you look at. You could also say, look at the difference between 35 and 44, which is 9 million, right? That's 9 million. Over how many years?
Years.
What's the difference between 9 million over 8 years and 2.25 and 2.25 over 2 years? What's the difference? Trick question.
They're the same.
There is no difference. It's the same. It's exactly the same, isn't it? Think about it. 2.25 divided by 2 is 1.125. This is 1.125 million per year. Which is the same as that is. 1.125 million per year. You could also break them into 4-year increments. It doesn't matter how you break them up. It matters not at all how you break them up. Because we're assuming the data is what?
Linear.
Linear. That means, think about back to our discussion. Oh my God, it ties right into grade. I had a big right triangle on the board last week. I said, it doesn't matter what units you use, miles, kilometers, inches, feet. Remember all those different triangles we drew? All those different triangles we drew? It doesn't matter how big or how small they are. When you divide the rise and the run, the resultant quotient was always what? Always the same. Same thing happens here. This triangle would be 4 times as long as this triangle, because 8 is 4 times 2. But if you actually envision, and I will slide back up so we can see this, if you actually envision the triangle, okay, here's David's triangle. Follow me now? Follow me so far? This is an increase of 9 million over 8 years. Where would 2.25 be? Where would 2.25 be, friends? Say that again? Every 2 years, correct? Every 2 years. So you come out this way, you'd have one there, you'd have one here, you'd have one here, and each of these increases is going to be about your 2.25 million. It's not exactly correct because I'm not drawing it perfectly. It's more like 2 million showed on the graphic here. But each one of those, every 2 years, 2.25. 2 years, 2.25. 2 years, 2.25. 2 years, 2.25, and it gets you up there to 9. Or you just do the whole thing. 8 years, 9 million. Doesn't matter to me. Doesn't matter to me. So, I think we're agreeing. This looks like a linear model, yes?
Yes.
This looks like a linear model. Okay, so now the question is,
Doing it by 8s and 2s kind of butts because we haven't made an odd number of years this year.
that's okay. If we had the equation, though, it wouldn't matter what year we picked, right, Benji? So Benji's got a good point. He's like, we're an odd number year. 2013 is weird. Doesn't follow the 2. I think we don't have to worry about that.
No.
I think we don't have to worry about that. I think we, as long as we can get whatever linear model that we're hinting at here, once we have it, because what we want, let's put this on the sideboard, we want a goal. And the goal is to develop an equation. Now that we've decided it's linear, yes, we've decided the data is linear. Yay! Yay! You've just got 99% of your work done, honestly. Getting the data and knowing what to do with it is 99% of statistical work. Actually doing the processing takes no time at all, believe it or not. It's going to take us a while while we're learning it right now, but once you get this under your belt, no problems at all. We now need to know what equation best represents it.
Wouldn't it be a linear equation?
Yes! So it will definitely will be, but which particular one? So we have a vote for y equals slope times x plus y-intercept. That's what a linear equation looks like, right? You probably called it mx plus b back in the day. That's what we want it to look like. My question, what's the slope? What's the y-intercept? Please,
Well, we already know the slope because we have.
we're going to use the slope 2.25.
Over 2 over 2 or.
Over 2 or 1.125 over 1. I love
Or
it.
9/8.
So, but we're 9/8. That's even better, isn't it? 9/8.
I like 9/8.
I like 9/8. Probably easier to use that way. So vote number 1. We just use y equals. Now I'm going to write this out kind of wordily, and that's okay. Because one of the things I harp on in this class is the interpretation of slope, which I know you didn't do a whole lot of in your algebra classes. You just call the slope 9/8, and that's totally fine. I want to make sure you know what 9/8 means. Okay? So when we say it's 9/8, it's 9 million people per 8 years. That's your slope. Times x. Now what's x going to be again?
One the years.
X is going to be how many years? X is how many years? And the reason we like that is because whatever that number is, unit-wise, the units are going to cancel the years over here and leave the millions behind, which is what we want. Millions of people. Plus the y-intercept. What's that going to be? What's that going to be? What do you think? What do you think?
Well, I just.
Yeah?
A linear regression on it.
Oh, good for you!
Points.
You used technology to actually do the...
I did it by hand.
Crap. Using all 5 points or using the 2 endpoints?
Just 2 in.
Whew! Well, thank God. Just get the piss out of you right there. I thought you did a linear regression in your head with 5 points. My mistake. That's painful. No, so if we just have the 2 points, we've got a point here, which is 2 comma 35, right? 2 comma 35. And we've got this point out here, which is what, 10, 43. Now we already know the slope between those 2 points. We already know the slope between those 2 points. Since we know the slope between those 2 points, we can use those 2 points to figure out what the y-intercept is, can't we? Hopefully you're having nightmares now about your algebra classes. In order to know what that y-intercept is, all we've got to do is back substitute one of the 2 points. Do we use the 1040?
I used the 10, 40.
That should be 44, shouldn't it? I'm sorry. 44. So, if we use 1044, that's going to be 44, yes? 44 million equals 9 million per 8 years. Times 10 years. Plus, I'm just going to put this as y for y-intercept for right now. That's what we're solving for. Now take a look. I'm leaving all these units in because it's a good thing to see. What happens to the years here and the years here?
Cancel out.
That's your unit agreement. They actually agree with each other. So you're dividing years off with years, and you're left with just millions of people, which is exactly what you want. You want millions of people at the end of the day. So you end up with 90 divided by 8. Let's see, 88 divided by 8 would be, what is that, 11?
11.25.
Thank you. I didn't quite get as far enough to 2 divided by 8 is 0.25. So now we got 44 million equals 11.25 million plus y.
Subtract.
Yes! Solve that thing for y, and we're going to get 32.75. Did I do that right? Did I do that right?
Yeah.
32.75, okay. 32.75 million is y. That is the point that we're calling the y-intercept. Which means if we go back to our actual graph, we can add that point, I think. We'll have to go below the graph a little bit there. And that's okay, we can live with that, can't we?
You know what?
What?
I stuck this into my stat.
You hold that thought. Because that's what takes more than 4 minutes
It's
to.
so close.
No, it's good, it's better. Believe it or
Well,
not.
I know, but it's so close. Okay.
Hold that thought, please. Wait, we can't do it in 4 minutes. I want to finish this up, though.
Okay, that's fine.
I want to finish vote number 1 up, and then talk about vote number 1. Okay, so now 32.75 would be right about, well, here's 30, that would be 32 right there, right? I think, 34, yeah. So right about here. That would be 0, 32.75.
So 1990.
So say that again?
1990.
In 1990, we would have reverse engineered there are about 32.75 million, roughly 33 million people without health insurance. And that, hopefully you see, fits perfectly in line. So I can draw this straight with a straight line here. Pretend that's straight. Just kind of pretend. So, that line right there is y equals 1.125x plus 32.75. That's 2. Not hieroglyphics. 32.75.
So if x equals 13, what is y?
Exactly! So now we, was it 13 or 23? 23, correct? So, the first thing, we can now answer the question. I asked how many uninsured there are in 2013. We now have a model that allows us to plug, if you will, a value in and get, if you will, a value out. So let's do it. Let's estimate how many uninsured in 2013. And then we're going to go. All we've got to do is figure out what has to go where. Here's our formula. Y is number of uninsured in millions. X is number of years past 1990. We know that, correct? We know that X is 23 because it's 2013. So all we do is we do Y equals 1.125 times 23 plus 32.75. What do we end up with? About
47.37.
47. Let's call it 47 million.
No, wait a second. That's not what I got.
Was that what you guys are getting?
58.
About 23. Oh, it's got to be. This is 20. This is at least 23.
I got
56, 57, 58. That's better. Thank you.
I put 13.
That's okay. 58 million. I'll call it 58. Thank you, guys. Should be about 58 million uninsured. Now, we'll leave you with this for the time being. No homework for tonight except to prepare for your exam on Wednesday, which does not have this on it. Next example. I want you to think, I could feel the energy draining in the room as we went through that. As soon as I put the graph on the board, and then as soon as I busted the slope, and then as soon as I started doing calculations, and here's the good news. 2 pieces of good news. Number 1, the line we just found can be improved upon. It's a good one, but there's a better one out there that's even more exact. That's number 1, good news. Number 2, the machines will find it for us exactly, and we don't have to. The little booklet I gave you guys today, bring that back with you on Wednesday. We'll play with that after the exam, okay? Rock on, email me if you get stuck. I will email you progress reports this afternoon. Okay, Doc? Have fun. Bueno.